Something that I forgot to emphasize in the last video is notice that the 3's and the 5's are not stacked up on top of each other, right? So if one strand says 3 on the left side, the other strand, the complementary strand, is going to have to say 5 on the left side. And I know that this is the 5 end because this is carbon number 5 at the end of the chain. On the template strand, we have 5 on the right side, which means on the complementary strand, we would have to have 3 on the right side. We have to have different numbers. They're the same number. They're parallel, not anti-parallel. And again, I know that this is the 3 side because I have carbon number 5, 4, 3 with its hydroxyl sticking out at the end of the chain. So this is the 3 side. When I go into replication in more detail, and we talk about the synthesis of a nucleic acid strand that's hundreds of nucleotides long, obviously I can't draw out every single nucleotide. That would take way too long. And it would make the illustration look way too complicated. So what I'm going to do instead is, instead of drawing the nucleotides, I'm just going to draw this part of the nucleotide, that part of the pentose sugar. This part actually has an oxygen right here. Right? And so by drawing these little gray arrows, I'm telling you, or I'm showing you, what the orientation is. And then what I'll do is I'll draw a line through. And so you can see what the orientation of the nucleotides are, and you can quickly identify which end is the 5 end and which end is the 3 end. Right? So it would look, whoops, it would look something like this. Right? So let's get some practice, because you need to be able to decipher this way of drawing nucleotides. Let me draw this. Can you identify which end is which? All right, let me draw the nucleotides at the end of each strand. Let me actually try to make this look just a little bit cleaner. Okay, so this end is the 5 on the top left. On the top right, it's 3. Bottom left, 3. Bottom right, 5. And the reason I know that is because if I draw out the nucleotide, it would look like that and that. Right, so this is the 3 end, this right here, the 5 end. On my opposite strand, here's the 5 end, and here's the 3 end. Okay, what about this? Let's pretend there are hundreds of nucleotides in between, and I'm only drawing the very last one on the left and the very last one on the right. And then for this one, the complementary strand, I would need to do something like this. All right, this is 3. Top left, top right is 5. Bottom left is 5. Bottom right is 3. And again, if I draw out the nucleotides, you can hopefully see that. Okay, what about this? So instead of drawing it on its side, whoops, I'm going to draw it vertically. And then what about this? Uh-oh. Okay, let's look over here first. So this is 5, bottom is 3, over here's 3, down here's 5. Skip this if you need to in the video, but I'm going to draw it out again just to make it clear. It's the 5, that's the 3, 5, 3. Over here, 5, 3, 5, 3. No good. These strands are parallel. Parallel DNA unzips, and that is not good. If you unzip the DNA and it's not controlled, like if it's just randomly unzipping, the bases become exposed, they become susceptible to changing, you have massive amounts of mutations, it's just overall a very bad thing. Right, so natural selection has favored anti-parallel configuration because a parallel configuration makes the DNA not very good at its job. And the job of DNA is to conserve, to store, and transmit information. The best way to do that is by having it anti-parallel. Okay, that's all for this video. I just want to make sure that you understand what these illustrations are referring to. That's it.